we can resume now. So now we'll see together some performance aspects. So far we talked about IP layer, transport layer, MAC layer, a bit about the application, but we didn't talk about the physical layer. We will not dive into the details of the physical layer, but today I will give you just some aspect of the bit of the of the physical layer that might impact the performance of the protocols that are used above the physical layer. So to start, so the first aspect that we need to be careful about it is the bit rate. The bit rate is the number of bits that can be transmitted within a time unit. And the unit of bit rate is bit per second, kilobit per second, megabit per second, gigabit per second, and now nowadays we can talk about terabit per second. These are the different units that we use. And another term to indicate the bit rate is that we use interchangeably with within our context, within the computer network or computer science context, is the bandwidth. Actually, formally, bandwidth means something else, but in our context, we use bandwidth to mean bit rate. But just to give you an idea, what does bandwidth mean formally? Actually, it's something that we use when we do some kind of spectral analysis of the channel. So we talk about the bandwidth of the signal, and we have the bandwidth is related to the bit rate by information theory. For example, we have this formula that links the maximum bit rate we can obtain to the bandwidth as a function of the signal to noise ratio. So if we have a good coding scheme, we might approach the max bit rate that we can achieve. If we are using a bad coding scheme, we might achieve only a fraction of the max bit rate that we can achieve for a given bandwidth. But anyway, from this slide, what we need to remember is that so we use bit rate and bandwidth interchangeably in our context to mean the number of bits that can be transmitted within time unit. Now, just to give you an example about the bit rate, so if you look at your laptop, for example, so now almost all laptops nowadays are shipped with an interface, a wired interface of 1 gigabit per second. So the bit rate of your wired interface is 1 gigabit per second. But if you are lucky and using a Cat6 Ethernet cable, you will be able to use this bit rate. But if you use another cable, which is, for example, Cat5, you will be able to use up to 100 megabit per second, and it's something that you cannot really distinguish between Cat5 and Cat6 unless you read what is written on the cable itself. Propagation time. So this is another aspect that we need to pay attention to, and this is related to the physical layer as well. So the propagation time is the time that the signal needs to travel from one node to another node. So when the signal is going from A to B, so the travel time, the propagation time is this time between S0 and T0. So it is simply defined by S0 minus T0, and it is related to the distance and to the celerity of the signal. So D, the propagation time, is Si minus Ti. If we look at this line, it is S0 minus T0, which is equal to D divided by C. D is the distance, the physical distance between A and B, and C is the speed of the signal in the used medium. In copper, for example, C equal to 2.3 times 10 to 8 meter per second. In fiber optic in glass, so it is slightly less. It is 2 times 10 to 8 meter per second. And a rule of thumb, so for every kilometer, you assume that the propagation time is 5 microseconds. So you have 5 microseconds per kilometer. Now, in this picture, in this figure, we can see that beside the propagation time, also we have the transmission time. So the transmit a signal that it is not zero. So the transmit a packet on the line, the transmission time is not zero. The transmission time is the number of bits that you can transmit. Actually, it's the time that you need to transmit a number of bits. So to understand this, let us move to the next slide. So transmission time to send X bits at a given bit rate. Question, time to send 1 megabyte at 10 kilobit per second. So what is the time we need to send 1 megabyte? So what is the transmission time for 1 megabyte over a line of 10 kilobit per second as bit rate? So I will close the poll in 5 seconds. I close the poll. So the majority is wrong. I expected that because there's a trick in the question. So the transmission time is simply the number of bits divided by the bit rate. The number of bits that we have, we talk about 1 megabyte and not 1 megabit. So 1 byte is 8 bits. So we need first to transform the bytes to bits, then to do the math. So the formula becomes 10 to 6 times 8. 8 is the number of bits per byte. So we transform to bits. Then we divide by the bit rate to obtain 800 seconds. So the answer is the correct answer is answer number 1. Now, what is the propagation time around the Earth using copper cables? So Paul, remember that, just a hint. So the length of the equator line is almost around 40,000 kilometers. Five seconds to close the poll. I close the poll. Apparently, people are still answering. Okay, I close. And the majority is correct. So the math, propagation time is the distance divided by the speed. So the distance is 40,000 kilometers divided okay, yeah, okay, so divided by the speed in the copper approximately, and we get 200 milliseconds. So what does this mean? This means that if you are communicating with a machine, with a server in Switzerland, and you are in Switzerland, if you see that the propagation time is 200 milliseconds, that's a problem because it's too much. Either the server is somewhere else, it's not in Switzerland, or there's a problem in the network or a congestion that's causing this delay. But if you are communicating with a machine, you are in Switzerland, communicating with a machine within Switzerland, so the delay, the propagation time should be of the order of few milliseconds up to few tens of milliseconds, including the delay, the queuing delay inside the routers.
I have a question. How did we know the speed in the copper?
Actually, it is the electrical signal speed.
Okay.
Yeah, so it is, yeah, it's just like the electrical signal speed. And the propagation delay has nothing to do with the bit rate. So the propagation delay is a function of the distance and the speed of the signal. The bit rate is something completely different. So the bit rate has to do with the technology, with the coding, with many things. So it is not, it's something completely different. Now I'm showing some numbers in different scenarios. So the first scenario is data center. We have 20 meters, the distance between two machines. The bit rate is 1 terabit per second. So the propagation is 0.1 microseconds. So when you look at this propagation time, you see, wow, it is too small, so it is negligible. We don't need to think about it. But compare the propagation time with the transmission time, because the bit rate is 1 terabit per second, so it is 10 to 12 bit per second. So the transmission is 0.008 microseconds. So the transmission is negligible compared to the propagation time. And in this scenario, our bottleneck is the propagation time, is the 0.1 microseconds. This is our bottleneck. If we take another scenario with ADSL, so the distance between two machines, 2 kilometers, bit rate 10 megabit per second, propagation is 0.01 milliseconds. So it is much larger than the one that within the data center. But in this case, this is not the bottleneck. The bottleneck is the transmission, which is of 0.8 milliseconds. So when we need to design a protocol, we need to be careful about the bottleneck that we have and the scenario where we are working. With modem, we have 20 kilometers, 10 kilobit per second. Propagation is a function of the distance and it is independent of the bit rate. So the distance increases, the propagation time increases. The transmission time here is 800 milliseconds. It's a function of the bit rate. So the bit rate decreases, the transmission time increases. And here again, the bottleneck is the transmission time. In the internet, if you are talking to the other side of the internet, the distance 20,000 kilometers over a bit rate of 1 megabit per second, the propagation is 100 milliseconds, and the transmission time is 8 milliseconds. So the bottleneck in this case is the propagation time. Now, throughput is the number of useful data bits that we can send within a time unit. To understand the difference between throughput and bitrate, let us take this example, because throughput is not the same as the bitrate. So bitrate actually is the bits that are sent on the physical channel. Throughput are the bits that are sent on the application level. So to understand this, let us take this example. Assume that we have an application that is sending 1 byte every time over UDP. UDP, what it does, it takes this byte, it creates a UDP datagram and sends the datagram to the other end with only 1 byte inside. Now, this is the byte that's taken from the application. To create the UDP datagram, UDP needs to add its own header, the UDP header. The UDP header is 8 bytes. So we have one useful data plus 8 bytes for the UDP header. This is an overhead. Again, we add 20 bytes for the IP header. Again, this is an overhead. And also we add 26 bytes for the MAC header. And again, this is a third overhead. So the total, instead of sending one byte of useful data, we are sending 53 bytes. So if you have a line with 64 kilobit per second, for example, so the useful data can take at most 1/53 of the available bit rate. So in the end, the throughput of this line, of this application, can be at most 1.2 kilobit per second, which is equal to 64 divided by 53 kilobit per second. For this application, that's sending 1 byte at a time, which is not efficient at all. So this why the throughput is less than bitrate usually, and there's another reason for that. It is related to the protocol that is used, and this is what we'll see in the next slide. But just before moving to the next slide, so the unit of the throughput is the same as the bitrate. So we measure the throughput in bit per second, kilobit per second, megabit per second, etc. Now let us see the impact of the protocol and the throughput. This is a very simple stop and go protocol. So this protocol, okay, we might use it just for reliability because it deploys acknowledgement. So A has a packet, it sends packet 1 to B. Packet B is receives packet 1, so it sends the acknowledgement. A sends packet 2. Packet 2 is lost, so there's no acknowledgement. After some timeout, A will understand that there's no acknowledgement. This means that the packet has been lost. It retransmits the packet. And then we have acknowledgement, and A continues transmitting other packets. Now, to understand the performance of this protocol, so let us look a bit into the details. So here we have some periodic behavior. So we have every data needs 1 cycle time to be sent. So within this cycle time, from the beginning of the transmission of the packet that A has till the end of receiving the acknowledgement, so it can send only this useful data. So this means that the throughput that we have is the useful data in bit divided by the cycle time, and the cycle time equal to T. This is the transmission time of the useful data, which is equal to L, the length of this packet divided by the bit rate. Then we have the two-way propagation time, round trip propagation time, 2D, then plus T prime, which is the transmission time of the acknowledgement. T prime equal to L prime divided by B. So to recap, so the throughput is the useful bits that are sent within a cycle time. So it is L divided by the cycle time, which is equal to T plus 2D plus T prime. Now, if you do some transformation to this formula just to make appear the inefficiency components, so we get the throughput equal to B, the bit rate, divided by 1 plus some inefficiency components. So if these inefficiency components equal to 0, the throughput will equal to the bit rate. But unfortunately, these components are not equal to 0. The first component is L prime to L. So it is related to the time wasted by receiving the acknowledgement. And the second component is 2dB divided by L. 2dB is related to the time that's wasted while waiting for the acknowledgement. So 2dB equals to the bit that would be transmitted by A during this time. And this component is called bandwidth delay product. So the bandwidth delay product in this scenario is the bit that A would transmit during this time while waiting to receive an acknowledgement. And if the bandwidth delay product is too large, as we can see here, so the throughput will be too low. So this is very important metric to that indicates the efficiency of this protocol with a given physical channel. Now let us go back to the numbers that we have seen previously. So here we have these 4 scenarios: data center, ADSL, modem, internet. Here we have the bottleneck is the propagation. Here we have the bottleneck is the transmission. Here again the propagation. Let us compute the throughput. Let us look at the performance of stop and go protocol. First of all, we compute the bandwidth delay product. With the data center, the bandwidth delay product is 200 kilobit per second. It's too large. Therefore, the efficiency of this protocol is very low. So the throughput is only 3.8% of the available bitrate. So we have a very huge bitrate here is 1 terabit per second, but what we can achieve with this protocol is only 3.8% because of the bandwidth delay product. With ADSL, so the bandwidth delay product is 1,000 times less than that with the data center. So the efficiency is very high. So the throughput can be up to 97% of the bit rate. With the modem, the bandwidth delay product, again, it is much less. It is 2-bit only, and the efficiency is almost 100%. With the internet, with a large propagation delay, so the bandwidth delay product is too large and the efficiency is very, very low. Now, the stop and go protocol, it is a reliable protocol, but it's a very simple one. But fortunately, it is not the one that is used in the internet. Fortunately, we have the majority of the traffic in the internet is using TCP, and TCP implements much smarter mechanism for reliability, and the efficiency of TCP is much higher than that of stop and go. Now let us move to the congestion control. So if you look at this image, so this is where an image of an intersection somewhere in the world. So as you can see, all cars are blocking all cars, so they're stuck. There's no traffic, so the throughput of this intersection is 0. So you can think about this intersection as if it is a router where all traffic is going through this intersection, and now the throughput is 0. There's nothing happening. Cars cannot move anymore because there's no traffic light. There's no mechanism to control this traffic, this congestion. And specifically, so here we have a peak hour. So this the time where we need the most to use the system that we have, where we have the highest load on the system, but the result is that the system collapses because there's no control on the system. There's nothing to control this traffic, and this is exactly what happens in the internet. If every source, if all sources start sending a greedy behavior, flooding the network, and without implementing any congestion control mechanism, the network cannot survive. So the network will collapse. And this is what we'll see in the end of this part. Now, let us just take this toy example. We have two sources communicating with two destinations, as S1 sending to D1, S2 sending to D2. They are behaving in a greedy way. This means that S1 and S2 send as much as they can. Here, the link is 100 kilobits per second. So S1 thinks that it has 100 kilobits per second reserved for it through the internet. So it starts sending at 100 kilobits per second. The same thing for S2. Here we have 1,000 kilobits per second, and S2 sends at 1,000 kilobits per second. Here the link, it's smaller. The bandwidth here is smaller than the sum of these two bandwidths. So this bandwidth, this link cannot afford the offered traffic from S1 and S2. So this means that we'll have in the end some losses here, and the acceptance ratio. So this link C3 will accept only some traffic of C1 and C2, and the acceptance ratio is the bandwidth of C3 divided by the sum of the offered traffic. So it is 110 kilobits per second divided by 100 plus 1,000 kilobits per second. This is the acceptance ratio. This acceptance ratio will be applied on both. It's the same. So here we apply the acceptance ratio to see what it remains from S1 traffic on this link, and the same thing for this link. Now, a question. So we have this scenario, two greedy sources sending as much as they can, and what would be the throughput that D1 can receive from S1? Okay, so I will close the poll in 5 seconds. I close the poll. Let us see whether the majority is correct. So the majority says 100 kilobit per second, but I guess it is only 10 kilobit per second. Let us see. So the acceptance ratio is the bandwidth of C3 divided by the sum of the offered traffic. So 110 divided by 1100 is only 10%. This means that C3 will accept only 10% of this traffic. So we'll have only 10 kilobit per second for S1 on this link. And now on this link, we have the bandwidth is 100 kilobit per second. So it's much larger than the traffic accepted for S1 here. So at this node, we have a queue for this link. And for this queue, there will be no loss because the offered traffic is less than the available bandwidth. So in the end, D1 is able to have only 10 kilobit per second from S1 instead of the 100 kilobit per second that are sent by S1.
Excellent.
Yes.
Why you say 10% accepted traffic? So 10% of what value exactly?
Yeah, of the offered traffic. So here we have, so first of all, so this is 10% of the total offered traffic. The total offered traffic is the one of S1 and the one of S2. But we said that we assume that this accepted ratio will be applied on both. This means that we'll have 10% of this link and 10% of this link. So if we take 10% of the 10% of C1 of the offered traffic through C1, we'll get 10 for S1, and if we take 10% of the link C2, we'll get 100. So the total, the accepted traffic, is equal to the available bandwidth.
Okay, and why you say that you have only 10 that enters?
I said 10 from S1, but you still have 100 from S2.
Oh, okay.
So this 10 from S1. So if you follow the line, so the line here, the orange line, so it goes like this. Now it's thinner because now we have only 1/10 of the offered traffic, and it continues to D1. But also for S2, you have this line. Now it's thinner. We have only 100. Then in the end, it's much thinner and it will reach D2. It's clear?
Why it is 100% rate of transmission between C3 and C4? You said it is larger, but as I see, it is smaller because 100 kilobytes is smaller than 110 kilobytes per second.
Sorry, say it again.
I see that 100 kilobytes is smaller than 110 kilobytes per second. C4 is smaller than C3. So I don't know why the transmission is 100%. Maybe it's 90 or...
No. Okay. So here the bandwidth is 100 kilobit per second.
Yeah.
And X is the what we get is the throughput that we get for S1X.
Okay.
Here this is the bandwidth, and this is the throughput of S1 on this link. So the throughput of S1 is the same as the accepted traffic on this link, because here the accepted traffic is 10 kilobit per second. Here the bandwidth of this link is much larger. This means that this node will accept all this traffic and send it to D1.
Why is it much larger? Because I see that 100 kilobytes is smaller than 110.
We gave you, so here we said we gave you a link having this bandwidth. So
Okay.
the speed, the capacity of this link is 100 kilobit per second. This is something that we give. It's
Okay.
not something that we compute.
Okay. And
Okay.
it is receiving 10.
It's receiving 10 because here we have only 10 from S1.
Is it is 10 kilobyte, not 10, is it 10 kilobytes per second?
10 kilobit per second, yes.
Okay.
Exactly,
Okay,
10 kilobit per second, exactly, yes.
And it is also receiving, like, what is it? D2 is receiving also 10 kilobit per second from C1.
It's receiving 10 kilobit per second. Yeah, I coming to that. I will explain this. Yeah, exactly. Actually, this is what I want to ask actually. Here we have S2 is having 100 kilobit per second on C3,
Okay.
but
Okay.
the link here can afford up to 10 kilobit per.
Okay. I understand.
You
Okay,
see?
I
And
see.
in
Okay.
in this case, the acceptance ratio is the available bandwidth divided by the offered traffic. So the acceptance ratio is 10 divided by 100, so it's 10%. In the end, we get only 10% of this.
Let's go through this.
Can be accepted on this link.
Okay, thank you.
Most
Yes, perfect.
Okay, so yeah, so this is the answer. So the correct answer is answer 1. Now, so the take-home message of this is that greedy sources may be inefficient. In this scenario, we see that both sources behaved in a greedy way, but in the end, they couldn't really achieve a good allocation of traffic on the network. But if S2 were able to see that there's a bottleneck here of only 10 kilobit per second, so it would adapt its throughput. So it does not need really to send 10 kilobit per second. It sends only 10 kilobit per second through this link. So that 10 kilobit per second can go to D2, but this will give 100 kilobit per second to S1. So if S2 adapts its a throughput to the bottleneck that we have here, so S1 is able to send 100 kilobit per second here. It will get again here 100 kilobit per second, and in the end D1, the throughput at D1 will be 100 kilobit per second. But unfortunately, so the S1, S2 don't have an overview of that network, and that's why they behave in that way. But TCP allows us, there's a mechanism of congestion control with TCP that allows us to detect whether there's a bottleneck or whether there's a congestion, and to adapt the throughput of TCP to the network conditions. Now, let us understand the congestion collapse, how the system can collapse. Here we have, it is an academic example. We have a ring network. So it is symmetric. At every node, we have a source that is injecting lambda bit per second. So here we have lambda, the red one. Here we have lambda, the blue, the green. And at every node, we have a lambda that's injected in the network. And the destination of this traffic that's injected by source I is the source I plus 2. So this means that the traffic, the fresh traffic that is injected will go only through 2 links, and then it will get out of the network. And then we have, so the injected traffic is lambda. Here, in case we have losses, lambda becomes lambda prime. Again here, in case we have losses, lambda prime becomes lambda second, and then it gets out of the network as lambda second. The same thing for lambda, the blue lambda. So lambda becomes here lambda prime, and here after this node it becomes lambda seconds, and then it gets out of the network as lambda seconds. And on every link we have only 2, or every link is shared between only 2 traffic. So for example, if we take the link I is shared between the fresh traffic coming from the red lambda and the traffic that coming from the blue lambda. So it means that it's shared only between lambda prime in red and lambda second in the blue. So every link is shared between only two traffics, between lambda prime and lambda second. Now, in case lambda is less than C divided by 2, C is the bit rate of the link. So all links have the same bit rate, which is C. If lambda is less than C divided by 2, we don't have any congestion. There's no problem because the offered traffic is less than the capacity. So remember that every link is shared between only two traffic. So if the traffic is the sum of the traffic is less than the capacity of the link, there's no problem. So lambda second will be equal to lambda. There will be no loss. So lambda, it will be equal to lambda prime equal to lambda seconds, if lambda is less than C divided by 2. Now, if lambda is larger than C divided by 2, so we apply the same thing that we learned in the previous scenario. So we need to compute the acceptance ratio. In this case, for example, the acceptance ratio is the available bandwidth divided by the offered traffic. So the available bandwidth is C divided by the offered traffic. The offered traffic is the fresh traffic lambda and lambda prime. So C divided by lambda and lambda prime. This is the acceptance ratio. So if we apply this acceptance ratio on the red lambda, we get, so lambda prime equal to the acceptance ratio multiplied by lambda. So lambda prime equal to the acceptance ratio multiplied by lambda. The same thing, lambda second will be is equal to the acceptance ratio multiplied by the offered traffic, which is lambda prime. And now we have two equations with two unknown, because C is known, lambda is known. The only unknown variables are lambda prime and lambda seconds. If we solve this problem, we obtain this formula. And with some transformation, we get lambda seconds equal to C square over lambda plus something. If we plot this formula, so here we have lambda, here we have a threshold. So here we have lambda equal C over 2. And here we have lambda seconds. So here the fresh traffic that gets into the network, and here the traffic that gets out of the network. When lambda is less than C over 2, we have a linear increase between lambda and lambda second. Actually, lambda equal lambda second. So when lambda becomes larger than C over 2, we apply this formula, and we can see that the system starts collapsing. So when lambda becomes too large, so the throughput of the system becomes 0. So this is an example of a congestion collapse, and this is why we need to apply mechanism to control the throughput that goes into the network according to the network conditions. Otherwise, the network will collapse. So take-home message. This is congestion collapse. So this means that if we increase, when the load on the network increases, the network will collapse if there's no mechanism to control the traffic, to adapt the traffic according to the network conditions. Now, fortunately, the network does not collapse. The internet is not collapsing. Why? Because as I have already mentioned, so with TCP, the majority of the traffic in the internet is TCP. So the TCP controls the throughput of the source according to the network conditions. According to the network conditions, if the network is congested, TCP reduces the throughput. If the network is not congested, TCP allow to increase the throughput so that we can increase the utilization of the network. And how does it work? How TCP knows that the network is congested or not? Actually, TCP look at the packet loss. If there's a packet loss, it interprets this packet loss as a sign of congestion. So whenever a packet is lost, it reduces drastically its throughput, because for TCP now there's a congestion. We need to reduce the throughput in order to adapt to the network conditions, and then it starts increasing the throughput very slowly so that it avoid any congestion. And with TCP, usually we talk about multiplicative decrease, additive increase, or additive increase, multiplicative decrease. What does this mean? When we have a sign of congestion, this means that when we have a packet that's lost, TCP reduces the throughput, it divides the throughput by 2, so it multiplies its throughput by 0.5, and then as long as there's no loss, so this means that for TCP, the packet is good, it starts increasing the throughput gradually, very slowly. That's why we call it additive increase. Now, I will not go into details, because just to explain that, I need a full session to explain the congestion control mechanism of TCP. But just what we need to remember from this is that TCP, the congestion control mechanism of TCP, adapts the throughput of the source to the network conditions. And fortunately, that the majority of the traffic is TCP, because on some real-time applications use UDP. UDP does not care about the network conditions, and if if the majority of traffic on the internet is UDP, this would kill the network. The network would collapse if there's no other mechanism on the application layer that adapts the throughput to the network conditions. I think we are done, so I will stop here. So thank you very much. If there's no question, so we can close the session.